Today, I want to discuss about relation between automorphism and derivations on some non-commutative algebra. So this topic is in purely algebraic and not number theory. But today I want to discuss. Okay, first let me write down the title of my talk. Derivations and automorphisms. The algebra of non-commutative formal power series. In the beginning, first, let me introduce the contents of this talk. So, in general, if we have an algebra R over field K, so algebra means the associative algebra. Today, I assume K is a base field of characteristics 0. If we have an algebra R, we can consider the two important classes of linear operations. One is algebra automorphism. The other one is a derivation. So, by definition, algebra automorphism is as you know, this is a map from R to R, and the K linear isomorphism preserves the product structure. So R is algebra, so R has a product structure. So for any element x, y in R, this is the definition of algebra automorphism. On the other hand, derivation is a linear map on R, satisfy the Leibniz rule. dxy plus x dy. If R is a commutative algebra, then we don't have to care about the order of the product. But today I want to consider the non-commutative algebra, so the order is important. Anyway, when we have an algebra, we can consider the two important classes of morphism. So what's the relation of these two classes? The answer is if R has a good property, actually R has a good topology, then we can define exponential map from here to here and logarithm map from here to here, and one can make a one-to-one correspondence between these two classes. The definition of exponential is a usual one. So E exponential d is the infinite sum if d is a derivation, this map satisfies this property. This element automatically defines automorphism. But here we have to consider the infinite sum of operations. So we need a topology on the R or on the space of operations. So in general, we cannot define such kind of one-to-one correspondence. But if R has a good property, then we can make a one-to-one correspondence. Today, I want to choose a algebra of non-commutative power series in two variables as R. So usually the algebra is denoted by this symbol. Here R is a non-commutative algebra of formal power series. Over K in two variables over K. So and this algebra has a natural grading. So this algebra has a natural topology. Then so we can define the exponential map and also logarithm map. So today's topic is, first, I define the specific class of derivations. Then we can compute the corresponding automorphism associated to the derivation via exponential logarithm correspondence. First, define the specific derivations. Second, compute. Via exponential map. So the reason why I choose such kind of algebra, the first reason is this algebra, non-commutative formal series algebra, is a typical example of the complete augmented algebra. In a sense, this is the most simple example. Non-commutative augmented or augmented algebra or Hopf algebra. So today I don't say the definition of augmented algebra, but any augmented algebra is quotient of the algebra of formal power series. So of course one variable case is most easier, but non-commutative two variable is the most simple case. And the research is motivated by another field. Actually, this algebra can be regarded. Oh, sorry. D. If one make a correspondence A and this one, this differential form and this differential form, so this means this relates to some geometry. So this is a projective line minus 3 point. The regular differential form is spanned by these two elements. Consider the disk space and consider the tensor product, tensor algebra of this one, and also consider completion. Then, so such kind of object is related to the polylogarithm. Actually, this relates to the multivariable version of polylogarithm. Or my original research area, multiple data values. Unfortunately, there are no essential application of today's result to such kind of theory, but hopefully, near future, I want to find the application of today's result to such kind of theory. Anyway, this is the content of this talk. Okay. Before starting the content, first let's show the example of the calculation of exponential map. If D is a derivation on this algebra defined by A equal A squared, the image of B is AB. Please keep in mind that the derivation also automorphism on this algebra is uniquely determined by the value on generating set A and B. If we fix the image of A and B using a product structure, this property, we can extend the definition on the all element of R, also using a Leibniz rule. It's the same situation. So derivation on R is uniquely determined So I just defined the image of generators A and B. Then this is the exercise. So what's the corresponding automorphism? Automorphism is also characterized by the image of the generators. So what's the EDA and what's the exponential DOB? In this case, the computation is quite easy. The answer is 1 minus A inverse A. And the image of B is 1 minus A inverse B. Because to calculate the exponential, we have to calculate the nth composition of D. But in this case, using a mathematics induction, it's easy to predict these images. Using this formula, it is easy. Please note that now we are in the non-commutative world, so the order of the product is important. But if we define the more complicated derivation, the calculation is very difficult. For example,
when you say the inverse of 1 minus A, you actually think of 1 plus A plus A.
Yes, thank you. So sometimes in this talk, I use such kind of rational the notation of rational functions, but we always this element as a formal power series by considering the Taylor expansion at the origin. This is the second exercise, but I think this is not the exercise. It's a challenge program. It's very easy, right? If D is a derivation defined by, I should write the derivation here, derivation. Defined by, okay, this is the same as before, but AB minus BA plus 3 times B squared. In this case, the computation of nth composition, this was quite difficult. But I can write the answer. The image of A is the same, so the answer, the image of A of E to the D is the same, 1 minus A inverse A. But the image of B is more complicated. This is the answer. From the answer, you can guess the difficulties of the calculation, this one. The n plus 1 homogeneous element of this series is the answer. So actually, it is very difficult. So today's result is a generalization of such kind of result. So in other words, the pure combinatorics or pure algebraic or
there's some physical meaning of your challenging derivation.
which kind?
Physical.
Physical. Oh, yeah, yes. But not physical, but D has a geometric meaning. When we have a variety or manifold, to define the tangent space, we use derivation. The derivation on the function field at some point is defined tangent vector. So in the meaning, the derivation is, but in this case, R should be commutative algebra. But now in our case, R is a non-commutative algebra. So the corresponding geometry is more difficult. Actually, non-commutative differential geometry or non-commutative something. Okay, this is the introduction. Okay, section 1. Let me recall that R is a algebra of formal power series in 2 variables. And this ring has a natural topology. By using a degree. The degree of generator is 1. So this is a standard grade. Then we have a one-to-one correspondence between some subclass of derivation and some subclass of automorphism of R. Here R0, del 0 is a set of derivations and also D is a degree increasing map. This means the image of D, image of the generating set A and B. So A and B is the degree 1 element. So the image of DA, A and B should be the degree of this one should be larger than 1, larger than or equal to 2. So this is the terms of degree 2. A degree larger than or equal to 2. Right? For example, so this problem, the image of A is a degree 2 element, or so this example is a degree increasing derivation. And here, auto1 is a set of all automorphism, algebra automorphism. And delta is a unipotent map. Namely, delta A image of A is A plus higher degree term. So terms of degree 2. Larger than or equal to. Also, image of B is B plus higher degree term. This is the definition of unipotent. Or someone use a topologically unipotent map. Oh, sorry. So to define the exponential map, we have to consider the infinite sum of operations. If D is an increasing map, then D n's composition of Dn also increase the degrees. So it makes sense of the infinite sum. So we need this condition to define exponential and logarithm map. And also, please note that this set of operations has an algebraic structure. So this one has a group structure, and this one has a Lie algebra structure. By defining a bracket operation by here. Oh, where should I? Oh, yeah, here. Sorry. The bracket. So in general, composition of derivation is not derivation. But if you consider the usual additive bracket, then this operator satisfies the Jacobi identity again, and this defines the derivation. So by using this bracket, the set of derivations makes a Lie algebra. The basic field is K. Okay, it's time to define the other specific class of derivations. So my final hope is to calculate the first given any element of this one and calculate the corresponding automorphism. But unfortunately, the calculation is quite heavy. So today, I just consider the specific class of this Lie algebra. So for any natural number m and for any element of base field. So today I say scalars. Define the derivation dm. Actually, this derivation depends on the parameters by the image of A is A, the power of A, and image of B is alpha times am to the 1 plus beta a to the m b plus gamma b a to the m plus delta So this derivation is increase the degree m. So this is derivation which I want to consider today. Okay. The first theorem is a computation of the corresponding automorphism of this one. But before stating the theorem, first let me consider the structure of the real algebra spanned by these derivations.
You consider self-algebra of these dm generated by these dm's?
No, I consider the real algebra generated by all dm.
Okay. So
But the parameter alpha, beta, gamma, delta is fixed.
okay, fixed. Yes.
But the algebra is a sub-real algebra of this one. Okay. The following proposition is very interesting. For fixed parameters, so as I said before, the bracket of derivation is also bracket. So what's the dm and dm, bracket of dm and dm? This is also derivation. But this derivation is just a scalar multiple of dn plus m. For m and then larger than 1. As a second proposition, dm plus 1 can be written by iteration adjoint. How to say? T1. Here, the number of d1 is m minus 1. So, starting from the d2, then consider the adjoint of d1 bracket, d1 bracket, m1 minus 1 time, and after some multiplication by scalar, then we can express dm plus 1. So these two relations says that the real algebra spanned by dm is very simple. Actually, the proof of this equation is very easy because both hand side is a derivation. So we just check the image of the generator A and B. Then it is very you can very easy to show. First remark. So we use the script L is real algebra generated by dm. Here m runs over all positive numbers. This means consider the real algebra spanned by all dm. Here we always fix the parameters. And
just a quick question. Do we need to assume that alpha, beta, gamma, and delta are sufficiently general so that they don't satisfy some bad relationship? That is
no, we don't assume any condition. These are general parameters. But here, the definition, this is the element of this space is just a finite sum of dm's. But I want to consider the infinite sum of derivations, so we need a completion. So this is the definition of L. But actually, the second proposition says that the real algebra L is generated by D1 and D2. We don't need the other derivation. We just using just D1, D2. One can express the other derivations. So actually, this is a finitely generated, two-element generated real algebra. And as a second remark, so in usual, any bracket of any two element is 0, then the real algebra is called abelian real algebra or commutative real algebra. But this relation says that real algebra is not commutative. So if D and D prime is a commutative element, then it holds the following exponential formula. But this is wrong. But if D and D prime is commute each other, then this formula is true. But in our case, D and D prime may not commute, so this formula doesn't hold. So we need an extra term. As a classical result, someone compute such kind of series. The name is Hilbert series, I don't know, Hausdorff series, or Hausdorff-Campbell-Baker series. So usually, in textbook by Bourbaki, they use such kind of notation H. This H is the abbreviation of Hausdorff. Okay, this is a remark of the proposition. And also, I should mention that so this relation is known as a relation of classical bit algebra. So the relation. Okay. The relation one is the same as those of bit algebra.
Bit algebra okay?
No, this is the usual, not the usual bit algebra. So in analysis, so the definition of bit algebra is BD, such kind of algebra. So there are another concept of bit algebra in number theory, but this is a different one. So usually they consider the bit algebra over C. Okay. So our first goal is explicit description of the automorphism corresponding these derivation dm. So the first theorem is that the exponential of dm, this is the automorphism, is given by minus. This is an image of A. As I said before, this element can be considered as a Taylor expansion, as a formal power series by Taylor expansion. And the image of B is very complicated. Minus beta plus epsilon times B plus minus omega or minus minus 1 times sorry, I need a 2 line. Inverse. Yeah, the expression is quite long. Here, so alpha, beta, gamma, delta is a fixed parameter, but epsilon and omega is defined by forwards. Epsilon and epsilon prime. In this expression, there are no epsilon prime. Only appears epsilon only appears this equation, but this is the two roots of quadratic equations: t square plus beta plus gamma minus 1 to the t plus alpha delta. And omega is the difference of two elements. So by definition, epsilon dash, epsilon prime, and omega is element of a quadratic extension of K. But it is easy to check that the expression of the right-hand side is symmetric for epsilon and epsilon prime. So this element defines the coefficient of this element is in K. So actually this is an element of K. There are no contradiction. Yes, the expression is a little bit long.
How did you find?
It's just a good question. Actually, no one has a systematic way to find such kind of element. So just I found, I calculate the example, many example. For example, first I check the alpha equals 0 case, or almost or the 0 case. So and just I predict the form, but I can show this form is correct.
I have a very
Computer by
No, I didn't use 100.
I have a very stupid. Here you seem to be using the roots of unities over there, like minus, instead of minus 1, you have minus 1 over m. How do you define this one? Like just using the usual Taylor series expression?
Yes.
Okay, still. Okay.
You just use a binomial
Okay, minus
series.
Or binomial.
Yeah, so this defines the element of K, element of R. Yes.
Is Mathematica able to calculate noncommutative formal power series?
What mean?
Is Mathematica able to calculate noncommutative power series?
Mathematica. I think it's possible.
Okay.
But I didn't use, and I think if I use Mathematica, the discovery is more difficult. I think the expression is too long.
Okay.
Of course, I can check the lower degree term, but probably I cannot guess the rule. But this is a part of my result, because here dm is just one derivation. But as you know, the sum of derivation is also derivation. And so one can consider the exponential corresponding automorphism, because if this formula is true, it's easy to calculate the d plus exponential of d plus d1. But in our case, the formula is quite long. So the my next result is corresponding automorphism of any linear combination of dm. To consider the linear combination of dm, I need some good notation. Actually, this notation is used by Zagier. So let fx be. Yes.
Before we go further,
Yes.
let me ask some questions
Yes.
on this Lie algebra side.
Yes.
It seems to me quite interesting that is there some application to the theory of modular forms in order to find a solution of partial differential equation like ASARC did about 20 years ago? Dug into the several derivations, and he applies some derivation to the modular forms, and he found some solutions of partial differential equations by using the structure of the algebra.
Okay, I don't know such kind of derivation he defined, but at the moment I don't have any application. But so the derivation is connected to the, for example, Cohen-Rankin bracket or like this one. I see. At the moment I cannot say anything, but but this structure is quite simple, and so I think there are many research related to such kind of real algebra. Okay, let fx be the formal power series. Here I'm using another variables indeterminates x, but here Cm is a coefficient. But we have no constant term. So let me write x times usual formal power series. So k double bracket x is the usual formal power series. And, by multiplying x, this expresses the maximal ideal. So this set consists of the formal power series without constant term. For such kind of element, we define the derivation df by just replace xm, x to the m by dm. So this is the element of del 0.
Or n greater than or equal to 1?
Sorry, thank you. 1, yes. That part is important. Thank you. Actually, it's easy to check the image of df on generator is f a times a. Here, f is a formal power series, but this is a we consider the substitute. We substitute a to the x. So this is an element of R. Alpha fa a plus beta fab gamma b. Oh, sorry. Gamma plus delta of course one can define the derivation by this expression, but both definition is the same. Here fa has no constant term, so one can consider the division by a. This is also elements of R. So our goal is computation of the corresponding automorphism of this derivation. And please note that the image of A is written by a formal power series in A. Here, there are no B. So we have R. This is a 2. But as a subalgebra, we have a formal power series in A. So the derivation df can be restricted to this algebra because the image of A is written by A. The written is an element. Image of df is image of A of df is an element of this one. So one can consider restriction. So in this case, it's easy to show that df is a can be expressed by this form. Here, dA is the usual differential form, the differential operator in A. So if we have a formal power series in A, we can consider the usual derivation, formal differentiation. And after differentiation, consider the multiplication by FA times A. So the right-hand side is a derivation. The left side is also derivation. So after checking the image, one can easily check this equality. So this derivation is a very usual object, classical object, if we consider this derivation on this algebra. Actually, there are classical results by commutative.
So is this equality true on this subalgebra or everywhere?
No. It's important. Only on this subalgebra. So this equality doesn't hold on R. The result of commutative 1973, so this is a classical result. Someone compute the nth composition formula of df in this setting. The expression is a little bit long, but I'm sorry, I have to write because I need this definition of this element. Expression is complicated, so please neglect the detail. Just see the expression. Here Kj means Kj's derivative, differential derivative. Commutative is probably combinatorist in 1933. He published a textbook. The name is Combinatorial Analysis. I just forgot the detail, but he's a combinatorist. So he found such kind of formula. The formula is quite complicated, but it's true. Okay, so this means that we already know the image of automorphism D to the df, but we know the image of A, only A. So commutator already calculated A. But A is simple comparing the image of B. So okay. This is the definition, but in other words, this is the main result. For any element of formal power series, this symbol means formal power series in X whose constant term is 1. define automorphism delta H the expression is too long, so let me introduce another symbol, B, where image of A is already calculated by commutative. So using this notation, Tn, and AH is UH A beta plus epsilon times B plus minus omega and the BH inverse is 1 plus omega minus 1 omega A epsilon A minus delta B bracket to UHA gamma plus epsilon. I define all. Yes, this is the definition, and this is the answer of the corresponding automorphism. To state the theorem, let me call the remark. Here, I use the infinite sum of Tn. Unfortunately, there are no simple expression of this element in terms of elementary function. I checked several examples, but I found a function which cannot be expressed by elementary function. So, no simple expression of THA in terms of elementary function. In general. So in the case of theorem 1, so in that case, we can get the explicit form of the image of A. Do you remember this such kind of element? In that case, this is a UHA. So we can succeed to express this element by elementary function. But in general, we cannot get the expression. So this is the main theorem. For any power series without constant F, set H is exponential of F. This is an element of this space. Then exponential of df is delta H. So actually, this definition is the answer. I have not enough time to give a proof, but just okay. So this theorem says, I think this diagram is more easier to understand. Theorem 2 says so if we write this space by L. From L, so first fix the element small f. Then consider the exponential map. We have a H. This is a element of this one. So this set has also one-to-one correspondence via exponential and logarithm map. And for given f, we define a derivation. So here is a map D is a L or del 0 L. And also we consider the correspondence delta. Here is a, let me write a G. This is a by definition, this is the exponential of L. And we have a exponential logarithm map here. So that theorem says this diagram is commute. Unfortunately, so okay, so this is my result, and today I couldn't say the detail of the proof, but to give the proof, we need a more study about the structure of this diagram. For example, this has a trivial real algebra structure, commutative real algebra structure, but unfortunately the correspondence D is not real algebra homomorphism. But for example, this is not key. For example, we can show if we introduce another D bracket structure on L, then this correspondence D gives a real algebra homomorphism. Here, df, deg bracket is defined by df dx times g minus dg dx times f. So I think this is a little bit strange, but if we define a bracket structure by this equation, this satisfies the Jacobi identity, then so L has another non-trivial real algebra structure. So after such setup, we can show these are D homomorphism, and also we can introduce another group structure on G, and finally this diagram is let's say, is compatible. So this side, upper side is the real algebra structure, and the bottom side is a group structure. Each map, this is a D home, this is a group home. And after proving such kind of background, then we can show such kind of explicit computation. I'm sorry, today I cannot have that. Yeah, that's all. Thank you so much.
Are there some questions?